Now, the reason I didn't do this is because often for example, in a two force member, we do realize that if we see there is a element on which only two forces are acting, then just that knowledge helps us to determine or to make the problem simple without directly applying the equations of equilibrium. The conclusions from the equations of equilibrium that the forces will be equal and opposite and will act along the same line are sort of useful enough to be used. Now, similar to this, we have sometimes what is called a three force member, on which if we have, let us say, a link on which so now again in a three force member would be one on which forces are acting at 3 points and there is no couple, no moment. So, forces have to act at most at 3 points on this element. So, that is why the name comes three force member. So, let us write the definition. Forces act on the component at 3 points and no couple. Now, in this case, the conclusion we can draw is that so then please settle down. If we apply our equations of equilibrium, what we will get is that either the three forces which are there, now in this case forces are acting at points A, B and C, we can call it as a vector A, vector B and a tension T, suppose there was a string tied whose direction is known. So, then either the three forces have to be parallel. So, that means the forces at B and A also have to be along the line parallel to T if one of the forces is known, or so it could be either this case or the three forces have to meet at a particular point which could be anywhere in space, it need not be on the same member. So, in that case if you have this T and the force through A and B, they have to meet at some point if they are not parallel. So, this is the simplification which will come in case of a three force member, and in some problems, for example, in one of the problems which has been assigned to you in the sheet, you could also use this to make life simple, but the whole problem why it is not as easy is if the forces are concurrent, then what happens is that you have to find the point of concurrency, and locating that may not be easy. The point of concurrency is the three forces have to meet, and that you can only do if you know the directions of two forces. In this case you do not know the directions of A and B, so point of concurrency is not easy to find. But suppose the link at B is such that it has a roller joint, then you will know the direction of link at B. So, in that case of course, if the roller joint is horizontal, then you know that T and B will intersect at the point of the link, and therefore, the force at A also should pass through that point. So, that means you will know the direction of the force at A. So, that is how three force member can help things, but often the point of concurrency itself may not be easy to find, and then you may all find, in addition, rather than finding the point of concurrency, you take moments about A is equal to 0, moments about B is equal to 0, and that may be a easier way. So therefore, but sometimes if you find that two forces are parallel, then directly by looking at it you can say the third force also has to be parallel, which obviously you know, you put sigma fx is equal to 0. If two forces are along y, then if the third force also has an x component, that will be 0. So that is something common sense, but this may be used if you feel you can use it, you can use it, you are free to use it to solve problems in the exam if it makes life easy, but otherwise you can use moments. So this is one thing which I had not done, but I thought maybe you can, this is given in the book, but now we continue with our discussion on distributed forces, and here now today I want to focus my discussion on centroids. So now for centroid, we talk of centroid of an area, and how do we define the centroid? Of an area. Let us first define this, and this if for an area A, maybe I should also put if for an area A, the centroid is at a position capital R, then the way we define the centroid is that area multiplied by R is equal to summation of AI times Ri bar, where Ri bar is the centroid of each of these areas AI, or actually the more basic definition comes that in an area we choose an elemental area dA, and if its position vector is R, then we sum up over all these position vectors, then we get this, and in fact that is how we get the formula. So maybe I can draw a small cartoon. If this is an area A, then we choose a small element of area dA. This is the position vector R for the element of area dA, and we calculate, first we multiply R bar times the area dA, and then we add it up over all the elements, and that is what gives us, this is what is termed as the first moment of the area. We get the first moment and we divide the first moment by the total area, that gives us the centroid. Okay. Now there are many different versions of this formula, so in fact here I should also specify Ri bar is the centroid of A sub I. So we can work out the centroid. Now this is centroid of an area. We extend this concept to the first thing, center of mass. So this could be also of a volume. So then A will be replaced by a volume. So if we talk of a volume, A is replaced by V and dA is replaced by dV. So, this is how we talk of in terms of volume. So, this is centroid of an area. Now, we could think of terms like center of mass. Now, when we talk of center of mass, then what we will do is, instead of choosing an area, we choose a mass, we choose a basic mass dm, and once again if this mass is chosen like this has a position vector r. So, then the total mass times the position vector of center of mass, this will be equal to integral of the mass r dm. Let me just correct this. So, this is how we work out these things. Okay. So, now the difference now which comes is that dm is basically density times dv. Okay. Now, if the density is uniform, then the centroid of the volume is the same as the center of mass, but if the density is varying, then you will get a rho term here which may be a function of r, and then it could change. So, that is where the difference will come. So, dm I can write it as equal to rho dv. Seems to be a bit of a problem in the pen today. So, that is how we work this out. This is the center of mass. Now, we can extend this concept further to center of gravity. In center of gravity, what will happen? We will talk of the weight. So, therefore, what we will have is, instead of dm, we will have the weight of dm, which will be g times dm. Okay. And there the center of gravity will be different from center of mass if gravity is changing across the space. If gravity is not changing, center of mass will be the same as center of gravity. So, basically in all these concepts we are trying to find the centroid. That is what we are trying to do. So, given this, now let us try to work out centroids of some simple, let us see how to find centroids of areas. So, center of gravity, is this visible? I think so. Okay. The center of gravity is again an extension of these concepts, and let us see how we solve some typical problem. I think you would be knowing these, but you may not have seen a double integral. So, let us see. So, we have an example I will take. I have this line y is equal to x. And y is equal to x square, and we want to find the centroid of this area. Okay. So, now to find the centroid, the first thing we have to do is find the area itself. Okay. So, first step is to find the area. Now, we locate this point. So, if we draw this one, I locate the intersection point, this will be 1 comma 1, and then for area what I do is I choose a small rectangular element of length dx along x, dy along y. So, area is equal to integral dx dy. Now, when we have this double integral, I say integral dx, that means I will go along the x and I will integrate this. So, that means when I do this integral dx part first, so I look at this, Now, integral of dx, so that means when we integrate this, the first integral stays as it is dy. Now, integral of dx will give me what? There will be a limit on x from x1 to x2. Integral dx from x1 to x2 is what? Is nothing but x2 minus x1. Okay. Now, because I am integrating along x, this point is x2, this point is x1. Okay. The right point here is x2, the left point is x1. And x2 and x1 will be functions of y. So, what is x2? x2 is the right limit, which is this one, which is equal to y is equal to x square. So, x2 is equal to under root of y. So, this becomes equal to integral of under root of y minus x1. What is x1? x1 is nothing but y minus y dy. Now, what are the limits on y? Y goes from this corner 0 to 1. So, limits on y will be from 0 to 1. Okay. And this we can carry out, and when we get the answer, you will get this as some of you are really fast, calculated it, that is right, it is equal to 1 by 6. Now, the same thing could have also been done in a reverse way, and that is instead of taking dx dy, I could have also written the area as integral dy dx. Now, if I do it like this, then I am first integrating with respect to y. Now, y will go for a general step from y1 to y2. So, if I integrate with respect to y, what I will get here is integral of y2 minus y1 dx. Now, what is y2, what is y1? y2 is x, what is y1? X square dx, and x goes from 0 to 1. So, this will again, when I calculate this, you work out, obviously it will have to turn out to be the same. So, this is how we calculate the area. Now, this is, we have taken it as a small area dA. You may have used other ways to find this out, that is, instead of choosing a small area of dx dy, you could have chosen strips. You could have chosen a horizontal strip or a vertical strip, and actually you realize the horizontal, this is nothing but a vertical strip. This quantity which with the double integral, when you go inside the first step, is nothing but a vertical strip, and similarly in the other one, when we integrate with respect to x, the first thing is nothing but a horizontal strip. Okay. So, it is up to you, you think it of as strips, that is also fine, you use double integral, you use a double integral, it is up to you. If maybe sometimes in simple problems like this, taking strips is easier. Okay. Now, having done this, let us now see how do we calculate the centroid, and let us do it. So, if you have to calculate the centroid, this was the area. Now, to calculate the centroid, the x component of the centroid, we use a times x bar is equal to x dA. So, this I will write it as integral x dx dy. If I am using, so once again let me draw this picture here, we have this strip, we have an area, and we are integrating with respect to x first. So, now the limits on x will be from x1 to x2, y will go from 0 to 1. So, how do I integrate now? What is x dx? this becomes equal to integral from 0 to 1 x 2 square by 2 minus x 1 square by 2 dy. Okay. And this we will write it as equal to, I take the half outside, integral from 0 to 1. Now, what is x 2 square? X 2 square is y. What is x 1 square? Y square, because x is equal, x 1 is equal to y times dy. Is that clear? So, once we do that, we calculate this, and this will be equal to 1 by 12. Now, or I can have the second one, if I take it as integral x dy dx. I could also do it taking the vertical strips. So, when I do it taking the vertical strips, I will first have integral x dy. Now, what are the limits on y? Again, the limits on y will be from y1 to y2, x will be from 0 to 1. So, now how do I integrate this? So, this becomes integral from 0 to 1, x dy will just give me x times y2 minus y1 dx. And now, I put in the values of y2 minus y1. So, this becomes equal to integral from 0 to 1 x times y2 is equal to x, y1 is equal to x square dx, and this will give me, you can, I am not carrying out the integration for you, you can do that yourself, and that will give the same answer. So, now you have to keep in mind when you do it x dy, you have to integrate, when you are integrating with respect to y, keep x constant. So, you just get x times y, and y in the limits from y2 to y1 becomes y2 minus y1. Okay. Now, what if you were taking strips? If you were taking strips for the same thing, so I am showing you 4 methods of calculating the same thing. If you were taking so now your formula is x bar a is equal to integral x bar for the element dA, and again here x bar a is equal to x bar for the element dA. Now, dA in both, in this case, if this is, we call this as y2, isn't it? This was y2, this was y1. So, dA will be equal to y2 minus y1 into dx, and in this case dA will be equal to x2 minus x1 into dy. But now, you have to be careful. The careful part is, what is x bar of the element? In this case, x bar of the element is just x. In this case, in the second case, what is x bar of this element? So, now let us to determine the x bar of this element, this is x y, x y. So, here x bar of the element is nothing but x. What is the x bar of this element? This x bar of the element will be equal to, basically it is equal to, it turns out to be, you have to take the x of this point, x of this point, average of these. So, this one will be equal to x of this point is x1, x of this point is x2, and you have to take the half of this point, the coordinates of this point. So, what will be the coordinates of this point, x coordinate of the centroid. So, this x bar of the element is x coordinate of the centroid. What will this be? x2 x1 plus x2 by 2, because it will be x1 plus x1 plus x2 divided by 2. So, that will become equal to, so the coordinates of this will be x1 plus x2 divided by 2. Okay. So, you have to be careful. In case like this, it is you do not have a single x bar, because this horizontal x element has many x's. So, you have to take the x bar of the centroid. So, you have to use, in this case, when you take the x bar, it is just the x of that point, because all the points have the same x bar. And similarly, you can use this to calculate the y bar of the centroid, and I think there is one problem like this in the tutorial sheet. Okay. Now, some other things flow from this, and I just thought I would. Sometimes you have areas which are symmetric about a particular axis. So, for example, in the first case, we have an L shaped area, and if I draw the diagonal axis B B prime, then the area is symmetric with respect to the axis B B prime, in the sense that for every point P which is on one side of B B prime, there is a corresponding point P prime, such that the two distances from the perpendicular line to B B prime are equal. So, in cases like this, firstly what we determine is the moment of area with respect to the line of symmetry has to be 0. Why? Because whenever you take a distance on one side, on the other side you will get a negative component, you add up the two, you will get it to be a 0. Second conclusion which we get is that if an area possesses a line of symmetry, then the centroid has to lie on that line of symmetry. And going from that comes a third point, that if there are two lines of symmetry in an area, then the centroid has to be the intersection of these, because it has to lie along one line of symmetry, it has to lie along the second line of symmetry. So, the centroid of the area has to be the point of intersection of these two lines of symmetry. So, therefore, what we have is, so we can use these things to determine centroids of simple shapes. Now, the last point is not really that important, you can read it from the book. But if the centroid of an area will coincide with the centroid of symmetry, that is obvious. So, now there are certain, I do not think that I tried to draw, but it is not very visible here. You do not need to remember these, this is just taken from the book. You can have a look at that, and you do, if they are needed, they will be given to you in the exam, unless I ask you to calculate it by integration. So, these are centroids of some typical figures. Well, if it is a centroid of a rectangle or a square or a circle, it obviously is the center. There is no big deal. But then sometimes you have things like a quarter circle, half circle, quarter ellipse, half ellipse, a parabola and all, and maybe a sector of a circle. If these centroids are needed, then, and if you are supposed to use them only as values, then I will give them to you. Or the question could be to derive the centroid of this, then of course you have to derive it. But otherwise, at least in my course, you do not have to remember things. Formulas, if there are any complex formulas, will be provided to you. I do not want you remembering all these, and this is from the book. So, therefore, even though it is not very visible, it really does not matter. This is just to show that this is what we have for centroids. So, now, so that sort of sums up our discussion on the centroids, etc., on the distributed forces. And